We have two topics we're going to discuss today, and that would be dividing polynomials and finding greatest common factors. So in the previous section, we did do division with exponents, but we only had monomials. We didn't have any plus or minus signs in the problem. If you want to divide something with more than one term by a monomial, something with one term, the basic idea is you have to divide each term by that denominator. So in example 1a, if I want to divide the polynomial by 2a, I actually have to divide both terms by 2a. And so I'm just going to rewrite this problem as two separate division problems. Then I can use everything I learned in the previous section to do the division. First term, the 2's are going to cancel, and I could use the quotient rule on the a's, or I could just cancel one factor of a out, and that leaves me with a 1a to the third. Same idea on the second term. 6 divided by 2 is 3, and a squared divided by a is just a to the 1, so I get a minus 3a to the 1. Now these aren't like terms, I can't combine them, and so that's my final answer. So it's going to be the exact same process in examples B and C. I have 3 terms in the numerator, and I'm dividing by that monomial 4b. So I'm going to write this as 3 separate division problems. I have to divide all 3 terms by 4b. To do the division, I like to think of this as reducing fractions. So in the first term, one of the b's cancel, and there's nothing we can do with that 4. In the second term, the b's both cancel, and I can also reduce the 10 and the 4 by dividing both by 2, and that becomes a 5 over 2. And finally, in the last term, there are no b's that can cancel, but I can divide 20 by 4, and I get a 5, so I have a common factor of 4. Finally, I'll write down my final answer. The first term is just b to the 1 over 4. The second term is 5 halves, and the last term is 5 divided by b. Notice that if something is in the denominator, for example, in that last term, there was a b in the denominator, that b stays in the denominator. It doesn't move around. Once things are in the denominator, they stay there. All right, let's do one more example. I'm going to do the exact same thing here. I've got 3 terms in the numerator, and so I'm going to write this as 3 separate division problems. I have to divide each of these terms by the 4x squared y squared. To do the division, I'm going to do some canceling. 6 and 4 are both divisible by 2. That becomes a 3 over 2. I can cancel the x squareds out, and I can take one of the y's out. That leaves me with just a 3 in the numerator and a 2y in the denominator. Second term, 8 and 4 are both divisible by 4. I can cancel an x squared out. If I take 2 away from 4, I have 2 left over, so that's an x squared. And finally, I can just completely cancel those y squareds out. So in the numerator, all I'm left with is a 2x squared, and it looks like, I have nothing left in the denominator. So that second term is just 2x squared. Last term, the 4's cancel. I'm going to cancel an x squared out. If I take 2 away from 5, I've got an x to the third left, and I'll cancel a y squared out, and that leaves me with a y to the 1. I'm going to rewrite my answer down here where I have more room. So those are the first 2 terms I found, and now this last term, let's see, in the numerator we just have an x to the third, y to the 1. Oh, and that's it. There's nothing in the denominator. So I think the most important thing to remember with these division problems is you have to break it up, and you have to do multiple division problems. You have to divide each thing in the numerator, each term in the numerator, by that monomial in the denominator. We're going to switch gears a little bit for the second topic of today. We're going to be talking about greatest common factors, which is basically the largest number that all numbers are divisible by. So in other words, if I look at example 15a, I am trying to figure out, well, what number can I divide both 15 and 27 by? It's kind of like finding LCDs but backwards. We're actually looking for a smaller number. What are these numbers divisible by? And if you know off the top of your head, simply because you have your times table memorized, that's great. In this case, I know that both of these numbers are divisible by 3, and so that's my GCF. Now, if you're not sure what the answer is, you can always make these factoring trees. So 15 can be factored as 5 times 3, 27 is 9 times 3, and then 9 is 3 times 3. And then the idea is you take a look at the factoring trees and you look for any factors that are the same, and 3 is the only factor that's the same, so that's my GCF. I think the factoring trees are much more helpful when you have multiple numbers. Like, for example, we've got 30, 18, and 24. If you know the answer right away, that's great. You don't have to show any work. You can just write it down. But I'm going to create factoring trees. 30 is 5 times 2 times 3. 18 is 3 times 2 times 3. And 24 is 3 times 2 times 2. Then I'm going to take a look at my factoring trees, and I'm going to look for factors that are the same. I noticed right away all of these numbers have a factor of 2, and they also have a factor of 3. And that's the only thing they have in common. So that means my greatest common factor is 3 times 2, or 6, and 6 is what all of these numbers are divisible by. Now we can do the exact same thing if we have variables. I'm going to show you this problem the long way, and then I'll show you how I can get the answer a little bit faster. So if I create a factoring tree, and I didn't write that down this time, but I know that 10 is 2 times 5, and x to the third means we have x times x times x, and then we have a factor of y. So I have listed the factors of 10 x to the third y. Then I can do the exact same thing with the second term. The 15 is 3 times 5. There's an x squared and a y squared. So I just wrote out or listed all the factors. Then I can look for the factors that are the same, factors that are present in both of these, and I can multiply all of them together. I notice I have a common factor of 5, an x times x, which is x squared, and a y. So my GCF is 5x squared y. Now, if you don't want to write down all of the factors, sometimes that can be pretty time-consuming, you can look at the numbers separately and do that in your head. 15 and 10, those are divisible by 5. And then when you look at the variables, you can pick the one with the smaller exponent. Both have x's. The smaller exponent is 2. Both have y's. The smaller exponent is 1. So let's do one more example, and then we will take this a step further. So part D, rather than writing out the factors, I'm going to look at the pieces separately. So I have the numbers 11, 2, and 5. Those numbers don't have a common factor. There's nothing I can divide all those numbers by. And then I look at the variables. I have an a in the first two, but notice there's no a in that third term. So a is not a common factor. What about the b's? There's a b in the first one and the last one, but not the middle one. So b is not a common factor. If this happens, if you don't see a common factor, your common factor is actually 1. 1 is always something that you can pull out. Now, why are we finding greatest common factors? Because where we're going next is we're going to try to factor expressions, which basically means take an expression and write it as a product. So let's just do some examples. Example 3a says find the GCF and write in factored form. So I've got two terms to look at. I'm going to start by thinking about 3 and 6. Both of those numbers are divisible by 3. Then I look at the variables. They both have x's. The smaller exponent is 1, x to the 1. So my GCF would be 3x. To write this in factored form, the idea is you're going to pull the 3x out, or in other words, divide the 3x out, and write down what you're left with. So if I divide the first term, 3x squared by 3x, I'm just left with a 1x. And if I divide the second term, 6x by 3x, I'm just left with 2. And so that's my answer, 3x times x plus 2. Now, the great thing about factoring is you can always check your answer. I'm not going to do that here, but you could actually multiply. You could distribute the 3x and make sure you get what you started with. All right, let's take a look at a couple other examples. So GCF first, what are 8 and 32 divisible by? The answer is 8. Both of these have a's. Smaller exponent is a to the 1. Both have b's. Smaller exponent is b to the 1. So I'm going to take 8ab, I'm going to pull that out front, and to figure out what I have left over, I'm going to divide. 8 divided by 8 is 1, and if I take an a and a b out, I'm left with just an a and a b. 32 divided by 8 is 4, and I took the a and the b out, so there's my final answer, 8ab times ab minus 4. Same idea for example C. What is 36, 24, and 16 divisible by? I think it's 2. I'm not sure if there's anything greater than 2. Oh, maybe 4. If you're not sure, you can always make those factoring trees and look for your common factors. But I know that these three numbers are divisible by 4. I also see that all three numbers have, or all three terms have a y in them. Smallest exponent is 1, and that's all they have in common. So I'm going to take a 4y and pull that out front. If I divide the first term by 4y, I'm left with 9y. Second term is a minus 6x. Last term would be a plus 4. Now, you can also pull out GCFs that have multiple terms. For example, in part D, if I take a look at this problem, I see addition of two pieces. And what do those pieces have in common? Well, they both have an x plus 1 in them. And so you can actually treat the x plus 1 like your GCF and pull that out front. And if I take the x plus 1 out of the first term, I'm left with a 2x. If I take the x plus 1 out of the second term, I'm just left with the plus y. And there's my final answer. Now I want to show you one more example that I didn't put in my notes because this is something that sometimes throws people off. If I want to factor 10x squared plus 5x, my GCF would be 5x. I would pull that out front, and the first term would become a 2x. But what happens to the second term if we take a 5x out of it? It doesn't disappear. When we're factoring, we're technically dividing the 5x out, and so that second term is going to turn into a 1. So terms don't disappear when you factor. If you're dividing or factoring everything out, they turn into a 1. One thing that I keep in mind with factoring is if my original problem had 2 terms to begin with, inside the parenthesis, I should also have 2 terms. The number of terms shouldn't change. All right, that's it for this lesson. As always, let me know if you have any questions.